Hey guys, we're back again today with predicting products. Now this is one of the coolest things in chemistry because it allows you to look at two elements or compounds and determine what's going to happen to them in a chemical reaction, which is really cool, and it's one of the big things that chemistry tries to do is predict what's going to happen between two substances. And we're going to do that using the 5 types of reactions that we learned yesterday: synthesis, decomposition, single replacement, double replacement, and combustion. So you're really going to need to know what those types look like and how to identify them today. So if you don't know how to do that because you skipped yesterday, go back and watch yesterday's video because it's really important for today. But anyways, let's get right into it. The first type of reaction that we learned was synthesis. And synthesis was we're taking two things. Here we're going to just use two elements, and they're going to combine to form a new compound, and it's just going to be one of them. You're taking two things, putting them together. So our example here is sodium and chlorine, two elements. And synthesis says they're going to come together. So it's pretty easy to see that them coming together looks like NaCl. And that's a really familiar compound to you. It's sodium chloride, which is table salt, which you have known for probably a while. Now, anytime that you do synthesis or any of these reactions and you have a cation, which is a positive ion, like sodium becomes a cation because its ionic charge is +1, and an anion, like chlorine, which is or has an ionic charge of -1. Anytime you put a positive and a negative together, you have to balance the charges for them, just like we did in Unit 3 where we were doing naming and writing formulas. You probably already know the compound for sodium and chlorine is NaCl, but let's look at it with those charges. Now you have to find those charges on the periodic table. If you don't know how to do that, go look it up or find my video that's about that. But you'll see that sodium has a +1 charge because it's got one extra valence electron, and chlorine has a -1 because it's looking for another valence electron. Those charges are balanced with each other so that the total compound charge is 0. So you just write it as NaCl. Now, if we were doing some other elements that didn't have matching charges, like say we were doing sodium with oxygen, which is a -2. If they don't match, you'd have to take them and switch them down like this, so you get Na2O. But that's not the compound we're doing here, we're just doing NaCl, so we write it as NaCl. And then after you're done writing down the products, you have to balance the whole thing. You can see we've got 2 chlorines over here on the left, 1 chlorine on the right, so we have to add another sodium chloride on the right hand side to make 2 chlorines on each side. And then sodium has 2 on the right, just 1 on the left, so we got to add another one on the left to make it nice and balanced. And after you have balanced the whole thing, 2 sodiums on each side, 2 chlorines on each side, you count up the number and put the coefficient in front. Sodium is 2, chlorine gas is 1, and sodium chloride is 2. Decomposition is just the opposite of that. It occurs when a compound breaks up into its elements. And you can recognize these because you're starting with just one compound. There's nothing for it to react to, it's just going to split apart. So aluminum and chlorine are the elements in this compound, aluminum chloride. The only thing they can do is split up into their separate elements. So the first element here is aluminum. The next one is chlorine. Now there's something very special about chlorine gas. I'm going to have to pull up my periodic table in order to show it to you. All right, here it is. Now, if you don't already have it, go ahead and draw this on your periodic table. If you're watching this at home, then on your colored periodic table, you can get it back into Google Drawings and draw some lines on there. But over here on the right-hand side, there is a 7. And it's really 6 elements in the shape of a 7. that go together. These ones right here. On your table, you probably want to outline them instead of coloring them in because they're already colored in. This 7. And hydrogen is also included in this very special group. These elements are called diatomic. Diatomic elements mean they only occur naturally in pairs. And this is only when the element is by itself, not in a compound. So the one we're looking at in our problem right now is chlorine. So when chlorine appears by itself in a chemical reaction, when it's not part of a compound, a lone element, it always has to have a little 2. That's what diatomic means. 2, and atomic for atoms. It has 2 atoms always together. And all of these elements, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, do that. So if you write them down as a product, you have to make sure you include that little 2 on them. All right, so back to our... All right, so when we write aluminum and chlorine, chlorine is one of those diatomics, so you have to make it a little chlorine 2. Note that doesn't happen when it's inside a compound like NaCl. It's only when it's by itself as a product. So we've got some aluminum and some chlorine produced here, and we have to balance the whole thing. We've got 3 chlorines over on the left and 2 on the right, so you add another 2 on the right. However, that goes a little bit overboard. We've got 3 on the left and 4 on the right, so you have to add some more on the left, which gets it up to 6, and then some more on the right to get it up to 6. It's like seesawing back and forth between the 2. And then lastly, you got to balance the aluminum as well. There's 2 aluminums on the left, 1 on the right, so you add another one on the right. This one ends up having coefficients of 2, 1, 2, and 2, 1, 2, and 3. Next up, you got single replacement. Single replacement is identifiable because you got one element, a lone element, trying to break up this relationship that is the compound and steal an ion. And you have to decide which ion out of the compound the element's going to try to steal. You do that by looking at its charge. Potassium has a +1 charge, so it's trying to find something negative to join it because you need a positive with a negative here. And sodium, if you look at the periodic table, is also positive. So potassium does not want to get with sodium because it's also positive. 2 positives don't form compounds. But hydroxide, OH, is negative. So potassium is going to want to get with hydroxide, the negative. And what's going to happen is you'll get potassium taking the hydroxide, OH, and booting sodium out, leaving it all by itself, poor sodium. But as always, if you put a positive with a negative, you have to balance out the charges. Potassium is a +1. Hydroxide, if you look at your polyatomic ions list, is a -1. So those are happily balanced, and you don't have to do anything. How nice. And sodium is just sodium. It's not a diatomic molecule, so you leave it alone. And then you have to balance the thing. Looking at this one, it's already balanced, which is super nice. You just got 1, 1, 1, and 1. This was a lovely equation that didn't require much work. You just have to know to take the positive and have it steal the negative. However, there is a slight catch. If we go back to the relationship and dating metaphors, sodium and hydroxide are in the happy relationship here, and potassium is trying to steal hydroxide from sodium. This will only happen if potassium is more attractive than sodium is. If sodium is more attractive, then hydroxide is just going to stay with it and ignore all of potassium's advances. So we have this lovely thing called the activity series. The activity series is on your chart that has the polyatomic ions list. It's over on the other side, the right-hand side. And it is a list of the most attractive elements. Now, the most attractive ones are up here at the top. I'm going to put hottest or most attractive. And the worst, the least attractive are at the bottom. I'm not going to put ugliest because that's just rude. So We look at those two elements that we're trying to swap here, potassium and sodium. Potassium is found way up here. Potassium is a very, very, very hot metal, not temperature. We're talking attractiveness. And sodium is down here, still pretty hot, but not quite as hot as potassium. So potassium, the more attractive one, is going to win, is going to steal hydroxide away from sodium, so there is a reaction. If for some reason you had some products where the single was not as attractive as the one that was in the compound, you would write no reaction and move on with your day. Let's go look at another example for this. In this compound, we've got sodium bromide, NaBr, and a single element of fluorine, F2. Now, fluorine is a negative element, and negatives are trying to get with positives. So we go look at the compound. In the compound, sodium is a positive, because you go look on the chart, and bromine is a negative. So fluorine doesn't want to get with bromine, wants to get with sodium. So what's going to happen is that fluorine is going to kick bromine out of that relationship and get together with sodium. So you get sodium F, or sodium fluoride. Anytime that you put a positive with a negative, remember you have to balance charges. Lucky for us, sodium is a +1, fluorine's a -1, so they're already balanced and good. You don't have to add any subscripts. And that kicks bromine out on his own or her own, whichever. Now, bromine is one of those diatomic molecules, one of the special ones on the chart, so we have to add a little 2 for that one. Bromine 2. And then we balance out the entire equation. There's 2 bromines on the right, so you need 2 bromines on the left. Add a sodium bromide, which means you need 2 sodiums on each side. 2 are already on the left. You need 1 more on the right, which matches up with your fluorine 2 very nicely. So you have a 2, 1, 2, 1 equation. Now, checking to see if fluorine is able to kick bromine out and steal sodium is based on the electronegative periodic trend. We're not going to mess with that in this class. We'll just always give you one that reacts for nonmetals because there's not an activity series for nonmetals. It's just based off of electronegativity in the periodic table, which you may or may not remember. And if you don't remember, don't worry, because we're just always going to give you ones that react. Next up is double replacement. Double replacement, you can identify because it's got 2 compounds. It doesn't have any single elements. Let's go look at this first one. What you want to do in double replacement is split them into their positive and negative parts. For hydrochloric acid, HCl, positive part is hydrogen, and the negative part is chlorine. You can find these on the charges on the periodic table. For the other compound, sodium hydroxide, sodium is the positive, hydroxide is the negative. What happens in double replacement is that the positives are going to swap. So hydrogen, which is a positive, is going to swap with sodium and take the negative hydroxide, HOH, which is H2O. It's 2 H's and an O. It's water. And then sodium is going to take chlorine because that's the positive stealing the other negative. So you're going to have H2O plus NaCl, which sounds suspiciously like salt water. And then you have to make sure charges are balanced. With hydrogen, it's actually a covalent thing, so they share and don't transfer, but that's a weird exception. You can think of it just like hydrogen's a positive 1, OH is a negative 1. They're balanced and good, leave it alone. Same with sodium chloride, positive 1, negative 1. But you do have to check every single time you put a positive with a negative. Got to check the charges, make sure they're balanced. So those are good. Everything is balanced. It's a 1, 1, 1, 1. You can check that for yourself. Later on, you're going to be learning about precipitates and how to identify if one of these things is a precipitate, which is super fun. And it's going to use another chart, but we're going to look at that at a later date. Now let's go look down here at the bottom question. You've got a positive ammonium with a negative sulfur, and a positive lead with a negative acetate. The positives are going to switch, so NH4 is going to get with acetate. That's a ridiculously long compound. And anytime you put positive with negative, you balance the charges. NH4 is a +1, acetate's a -1. They're balanced and good. And then we go look at lead and sulfur. So this one is super fun. Sulfur, you know, is a -2. But lead is one of those weird ones that can have multiple charges. Even though it's not inside the transition metals, it can have multiple charges. So you're going to have to figure out its charge. And the way you do that is you look at it in the initial compound right here. So lead is paired up with acetate, and it's paired up with 2 acetates. Acetate has a -1, which means 2 acetates have a total of -2. And in order to balance that out and make the whole compound 0, lead has to have a +2 charge. So lead is going to have a +2 charge everywhere in the reaction. So over here, you can put a nice little +2. Those are already balanced and good. And we just have to balance the whole reaction. If you look at NH4 first, you can use it to balance because it's on both sides of the equation. NH4 has 2 on the left and 1 on the right, so you have to add another one on the right, which means you have to write out that whole crazy compound. So NH4s are good, 2 and 2. S's are 1 and 1. Lead is 1 and 1. Acetate is 2 and 2. So that's all balanced and good. It's 1, 1, 2, 1. All right, and last type of reaction is basically like dessert. It's so easy. Combustion, you can identify because it starts with some hydrocarbons, which is C plus H. Those are like methane, butane, propane, all those crazy named things. But it's got some combinations of carbon and hydrogen. Add them together with oxygen. The products are always CO2 and H2O. So you just write them down and balance. Don't even have to think about anything switching. Don't have to think about balancing charges. Just balance the equation. But sometimes, as we know, balancing these is gross. You want to save oxygen for last, usually save hydrogen for next to last, and do carbon first. So we got 3 carbons on the left. Got to make 3 carbons on the right. Cool beans. Then you've got 8 hydrogens on the left. Got to make 8 on the right. So you add some more H2O. And if you do everything well, your oxygens will work out very nicely. You've got 2, 4, 6, 7, 8, 9, 10 oxygens. Only 2 on the left, so you got to add 8 more with some O2s. So you get 1, 5, 3, 4 for your coefficients there. All right, guys, you should have practice in Google Classroom over this stuff, so get working on it. Please email if you have any questions. This is a very difficult topic, but it's exciting to know how to do it. So if you need help, please email or come to Google Meets or watch this video again.